Ever wondered how your favorite language model seems to remember what you said at the beginning of a conversation, even while you're rambling on and on? Well, it's not magic. It might be LSTMs. Welcome back to Learning Hub, where we unravel the mysteries of machine learning one layer at a time. I'm your host, and today we're diving deep into the fascinating world of long short-term memory networks, or LSTMs. So, in our previous videos, we explored the ins and outs of recurrent neural networks. We saw how they process sequential data, like text or time series, by maintaining a memory of past inputs. But RNNs have a little secret. They struggle to remember things from very far back in the sequence. This is the vanishing gradient problem, and that's where LSTMs comes to the rescue. Think of it like this. Imagine you're reading a long article, and halfway through, you forget what the main topic was at the beginning. Frustrating, right? RNNs feel your pain. LSTMs, on the other hand, are like that super organized friend who takes meticulous notes and never forgets a thing. So how do LSTMs achieve this memory superpower? The key is their special architecture. Instead of a single neural network layer like in a simple RNN, an LSTM has a more complex structure containing several interacting layers and gates. Now, we'll break down the key components. First, the cell state or the memory highway. This is the core of the LSTM. Think of it as a conveyor belt that carries information through the sequence. Information can flow along this cell state almost unchanged. Second, the forget gate. This gate decides what information to throw away from the cell state. It looks at the current input and the previous hidden state and outputs a number between 0 and 1 for each value in the cell state. A 0 means completely forget this, and a 1 means keep this information. So, we'll say you're reading a text and the topic changes from cats to dogs. The forget gate might decide that the information about cats is no longer relevant and should be forgotten. The third is the input gate. This gate decides what new information to store in this cell state. It has two parts. An input gate layer which decides which values will update, and a tanh layer that creates a vector of new candidate values that could be added to the state. Imagine you're learning a new language. The input gate decides which new words and grammar rules are important enough to remember. And lastly, the output gate. This gate decides what information to output from the LSTM cell based on the cell state and the current input. It filters the information and determines what the next hidden state should be. So, putting it all together, LSTMs use these gates to carefully manage the flow of information, allowing them to remember relevant information over long sequences and avoid the vanishing gradient problem. Now, we'll see a practical example of how LSTMs are used in real-world application. Instead of next word prediction in phones, we'll talk about something else. Consider sentiment analysis. Imagine you want to build a model that can automatically determine whether a movie review is positive or negative. LSTMs are perfectly suited for this task. The LSTM processes the review word by word, keeping track of the overall sentiment. The forget gate helps it discard irrelevant information, while the input gate helps it incorporate new sentiment-bearing words. Finally, the output gate produces a prediction of the overall sentiment of the review. Pretty cool, right? LSTMs are also used in machine translation, speech recognition, time series analysis, and many other applications where long-range dependencies are important. Now, I know what you're thinking. This is all great, but how do I actually implement an LSTM? Well, fear not. There are many excellent deep learning libraries like TensorFlow and PyTorch that make it easy to build and train LSTMs. We'll get into implementation detail in the future videos, so keep an eye out for more content on these topics. So to recap, LSTMs are a powerful type of RNN that overcomes the vanishing gradient problem by using a sophisticated gating mechanism to control the flow of information. They're used in a wide variety of applications, and they're a key tool for anyone working with sequential data. That's it for today's episode of Learning Hub. If you found this video helpful, please give it a like and subscribe to our channel for more exciting explorations of the world of machine learning. And don't forget to leave a comment below with your questions and suggestions for the future videos. What other neural network architectures do you want to learn about? Until next time, keep learning and keep innovating.